Hi everyone. In this video we are trying to do a different proof of infinitude of primes using Fermat numbers. For this we need some prerequisites. So our theorem is there are infinitely many primes. Okay, so the first thing we need is Pigeonhole principle. Pigeonhole principle. This is very easy. If there are n items are put into m containers, for example you have n greater than m, right? So then what we can infer, at least one container must contain more than one item, right? So here we have n pigeons and m holes, and if the number of pigeons are greater than the number of holes, then of course more than one pigeon should occupy one container, right? At least one container is there. So here you can see that I have illustrated using 9 containers and there are 10 pigeons, right? So first I tried to give each pigeon each single containers, but after 8 containers finished, I left with only one container but 2 pigeons. So I have to fill that container with 2 pigeon, right? So the theorem holds, right? Now you may have doubt that what if all pigeons can occupy one container? That's also possible. That does not contradict the theorem. What the theorem says, at least one container where it has more than one item, more than one pigeon, right? That happens in that case also. So let's keep this idea in our head. Okay, next we are going to do a lemma. So the lemma says it's like a if and only if condition. There exists a sequence of sequence fn of natural numbers such that the GCD of fi fj equal to 1 for all I not equal to j. If and only if the set of all primes are infinite, prime is infinite. So what is the property of that sequence? Any two numbers are co-prime, right? So any two in that sequence, if you take any two element, and that then the GCD of that two numbers are 1, right? Yeah. And if you can prove that such a sequence exists, if, then we can prove that the prime numbers are infinite. And the other way, if primes are infinite, then we can exhibit such a sequence. That's very easy. So let's assume primes are infinite. Then exhibiting a sequence fn is very easy. We let us take fn equal to pn, the nth prime, right? That is p1 p2 up to pn, and it goes to infinity. So if you look at this sequence, this sequence of primes, if you take any two primes and if you take the GCD, that would be 1, because you know that primes are the primes have only two divisors, the prime itself and 1. So the common divisor is of always 1, right? So proving infinity of primes to exhibiting such a sequence is easy. So what about the other way? Suppose we have a sequence fn such that this condition holds, like any two number you take, they are co-prime. Then we have to prove that primes are infinite, right? So let us suppose on the contrary that having said that this sequence exists, and we suppose that script p, the set of all primes, are finite, say p1 up to pn. Okay, so now consider n plus 1 elements from the sequence. We have fn, right? I'm taking on n plus 1 sequence elements, f1, f2 up to fn plus 1. Then we know that every fn or every number has a prime divisor. So definitely each fn n greater than or equal to 1 has a prime divisor, which is in fact in P, right? So the primes available is P1 to Pn. So each fn has prime divisors in P, script P. So this f1, f2, n plus 1 has a prime divisor from script P. Okay. Yeah. Now we use pigeonhole principle. So now let us apply pigeonhole principle here. So let us we know that in pigeonhole principle there are pigeons and holes, right? So here we can take the primes, n primes, as n holes, right? And f1, f2, fn plus 1, these n plus 1 sequential elements as n plus 1 pigeons. So this n plus 1 pigeons has to occupy the n primes. So what happens? So there is at least one hole contain more than one pigeon. That's what pigeonhole principle says. Here there is at least one prime P, right, contains more than one pigeon. That means more than one f values, sequential element from these numbers, right? So what is the meaning of that? So if you say like this, there is at least one prime P such that P is a divisor of at least two of f values. Let's say fi and fj, right? Let's take the minimum fi and fj. That means what? Fi and fj has a common divisor, which is a prime number. That means the GCD of fi and fj is at least P, so definitely greater than 1. That contradicts the fact that the GCD of fi and fj is 1. That's what we have constructed such a sequence, right? So that's a contradiction. So this contradiction happened because we assumed P is a finite set. But so what we can conclude, getting a contradiction, P is infinite. So set of all primes are infinite. So if you are able to exhibit such a sequence, then you are through, right? And now our question is there any sequence like that? Yeah. So now is there such a sequence? Yes, the sequence of Fermat numbers. So let us take fn to be 2 power n plus 1, right? So this is a number we have. My claim is the product of n minus 1, right, 0 to n minus 1 Fermat numbers, that is equal to fn minus 2, right? So this is my claim. We can use prove this using mathematical induction. So if you choose n equal to 1, then f1 can be find out like 5, and f0 is 2 power 2, that is 3, right? And what about this formula? This formula will changes like this: k equal to 0 to 0, because n is 1, so 1 minus 1 is 0, f1 minus 2. So f0 is equal to f1 minus 2, that is 3 equal to 5 minus 2. That's true. So 3 equal to 5 minus 2 is satisfying that recursive formula. So n equal to 1 is true. Now let's prove it using n plus 1 or n. So I'm considering the product from 0 to n fk, and I split like this: 0 to n minus 1 fk times fn. So that is fn minus 2 times fn. So if you do the calculation, you can see 2 power 2 power n plus 1 minus 1 times 2 power 2 power n plus 1. That will be reduced to 2 power 2 power n minus 1 times 2 power 2 power n plus 1. You can use a minus p times a plus p formula, a square minus p square. So that proves like you get last 2 power n plus 1 minus 1. If you rewrite this, you can prove that it is fn plus 1 minus 2. So that means it proves for n also. So my mathematical induction, this claim is true. Now how do we use this claim? That is, I have to prove that the GCD of any two Fermat number has to be 1. For that, what I am doing, I take fk and fn with k less than n. right? Two Fermat numbers were k less than n, and I use the formula. So I have a product fk and I have fn minus 2 in the right side. So the fk in my hand is contained in the left, right? So 2 can be written as fn minus the product containing fk. Since if we took now choose m, which is a divisor of fk and fn, and m is a divisor of fk, so m divides that product. M is a divisor of n, so m divides that fn, so it divides the difference, the right hand side. Okay, that means it should divide the left hand side, so m divides 2. That proves m equal to 1 or 2. But the problem is m cannot be 2 because Fermat numbers are odd. You can see Fermat number is designed like 2 power n plus 1, that means an even number plus 1. So Fermat numbers are odd. That proves whenever a common divisor exists for two Fermat numbers, that has to be 1. That means its GCD is 1. Then by lemma we have infinitely many primes, right? So in the next class we will study using elementary calculus. How can we prove this theorem, the infinitude of primes? So you can see my see the notes in my blog, and I have given the link in the description. Okay, thank you.